Welcome, my friends. This, what you see on the wall, is called an unfamiliar term to you at this moment. It's called a Voltaic cell. Excuse me. Of course, you're well aware of this already because so many of your electronic devices depend on something that we call a battery. So I'm not sure if you can see it from here. The term is Voltaic cell. A voltaic cell is a redox reaction. If you can see down here, I have a redox reaction, two forms of the redox reaction. It's as follows. I'm having free magnesium metal reacting with combined aluminum in a spontaneous fashion, meaning that eventually, it could be fast, it could be very slow, but eventually this reaction will happen. If you recall, this is called a single replacement reaction, in which a free metal replaces a combined metal in a compound and causes the free metal to become a combined metal and the combined metal to become a free metal. All right. We also have something called a net ionic equation, which eliminates anything that's not redox. If you recall, redox reactions only involve species that change their oxidation state. Now, notice here I have NO3 and NO3. NO3 is always -1 because it doesn't change its oxidation state. We call it a spectator. Let me use a different color just for contrast. Once you know what the charges are, now I've kind of given it away down here. Let's actually take a step back for a moment. Let's say you weren't given a nice net ionic equation here and you had to figure out what the charges were. Well, we have a free element here that has a charge of 0, and that's a free element that also has a charge of 0. We know that aluminum coming first in the compound has what we call a positive state. The nitrate has a negative state. It's always -1. In the compound that results, nitrate is still -1. The magnesium is a positive value. Now it turns out through algebra you could easily figure out what the charges were, but there's really no reason to do algebra because when you look up aluminum, aluminum is always +3 in a combined state and magnesium is always +2. Now, as I said a moment ago, getting a little ahead of myself, I said that because nitrate doesn't change its charge, it's eliminated. It's not part of the reaction. So if we're nice to you, we actually do the work for you in that case, and we give you a net ionic equation, in which we just show you those things that have a change in charge. So if you notice here, Mg0 is turning into Mg plus 2, and Al plus 3 is turning into Al0. They are both what we call the two halves of the overall reaction. And I just want to stay with the basics for this part of the video. What does it mean to be a battery? What do you have to have? Well, if you notice, you have two containers, two components, two chambers, which contain a solution. Now, this would be a classical battery, the first kind of battery that was created, that we've since refined them, but the redox principles remain the same. Now, if you notice, floating around in this solution, of a solution here and a solution here, I say this is silver nitrate solution, and this is magnesium nitrate. But I've emphasized that what we care about, what actually is part of the redox, is the aluminum plus 3 and the magnesium plus 2. Immersed in this solution and immersed in this solution are their corresponding metals, the aluminum 0, solid aluminum, and the magnesium 0. Notice that a wire, a metal wire, contains these two electrodes to each other. They're both called electrodes. But then we also are going to give them specific names based upon their function. And these, as I said, correspond to the ions in solution. I also have something called a salt bridge. The salt bridge is strictly for things that we call ions. Let me actually write this in. The salt bridge is for the migration of ions. We're not going to say much about what ions are going through, just suffice to say that it's necessary that ions be allowed to travel between the two sides. And as probably won't surprise you, through this metal wire, it is the electrons that travel. Now, the question for us right now, the main question is, well, how do I know which way the electrons are traveling? Actually, you might even ask, why is there a particular reaction between these two metals? Well, what we need to do, remember I said that we call this that's an electrode. Electrode. And this is also an electrode. I gave myself just enough space here. But they have specific names, both of which end in ode. Ode and ode. Now, it turns out that electrons are going to flow from a more reactive metal to a less reactive metal. Well, how do you know which metal is more reactive? Well, you go to something called Table J. I just extracted a few values from Table J. Notice magnesium is higher than aluminum is. So whatever's higher on Table J is what we call the anode. Remember what I said? These are both electrodes, but it turns out that this metal here is called specifically the anode. The less reactive metal, below it, is considered the cathode. So that's your first order of business, figuring what the anode is and what the cathode is. As I said a moment ago, electrons are going to flow through the wire from the more reactive metal, the anode, to the less reactive metal, the cathode. So with that, electrons are going to flow like so, in this direction through the wire. It's very important that you specify it's through the wire and not through the salt bridge. So that's the important point, the most important point, as I said, is determining what is the anode and what is the cathode. Now, remember we talked about these things called half reactions. And we want to say, well, what half reactions correspond to each of these metals? And I'm going to do that in a moment. And okay, I'm back. What I need to do is we need to talk about the difference between what we call the anode and the cathode. And what I was doing a moment ago is I made this little green poster, and it includes what we call a mnemonic device. It helps us remember things. It certainly helps me. The anox, think of two animals that are involved here, anox and red cat. What this means is that the anode is always where oxidation happens, and the cathode is always where reduction happens. All right, let's look at our two cells. We just said that the anode is here. It's involving the magnesium. Now there are two forms of magnesium. Notice I have magnesium plus 2 and magnesium 0, the solid metal. Well, then the question becomes, if I didn't have an overall reaction to base my judgment on, what is the oxidation happening there? Since anox, oxidation happens at the anode. Well, oxidation is always the increasing of the lower to the higher. So that must mean that the oxidation here is the Mg0 turning into Mg plus 2. Now, of course, we're not quite done yet. I just want to get the basic species up here. The cathode is this side. It involves aluminum. There are two species of aluminum. There's the aluminum floating around in solution, that's the AQ, and we have the aluminum 0 right there. Well, if you remember from reduction, we have a reduction of the charge from positive 3 to 0. So, let me write that here. That is Al positive 3 turning into Al 0. All right. Now, what maybe has jumped out at you, we've already talked about half reactions. I do have the same number of magnesiums on both sides, so it has conservation of mass, and I have the same number of aluminums. However, 0 does not equal positive 2, so I don't have something called conservation of charge. On this side too, positive 3 does not equal 0. I have a problem, I don't have conservation of charge. The only way that I can bring the two sides into balance is by putting electrons on the left or the right. Now my colleague, Mr. Weiss, came up with this little device. He's modest, he says, or I don't actually know, I have to check with him. Maybe he heard it from a colleague from a previous school. In any case, he shared it with us and it makes, it's a wonderful little trick. He asked the following, he said, class, in the word redox, what side is the ox on? And they say, of course, Mr. Weiss, ox is on the right side. What that reminds them is that electrons are going to go on the right side of the oxidation. Then he asked them, fine class, and on what side of redox is the red? And they say, Mr. Weiss, of course, the left side. That means I need to have one or more electrons on the right side, and left side, sorry, in order to balance this. Well, what do I need? 0 equals positive 2 plus negative 2, right? I need negative 2 for these to be equal, and that's going to be accomplished by having 2 electrons here. Down here, positive 3 plus negative 3 will equal 0, so I'm going to need 3 electrons here to accomplish that. Now, let me point something out to you. We know, I think you remember, that when you say oxidation, we have oil and we have rig. Oil, rig. Remember, this says oxidation is losing electrons. And that makes perfect sense to us because these electrons are on the product side, where they should be. Whereas here, rig, reduction is gaining electrons, and that thus makes sense that the electrons are on the reactant side. Reactant is gaining, product is losing. So this is an important skill in and of itself. If it says write the half reaction for oxidation, that's what you would write. If they said for this particular cell, write the half reaction for reduction, and this is what you would write as well. Now if you also notice, guys, down below, I apologize, it's getting a little bit cluttered down here, you have a net ionic reaction. So this means that you could look at this. This will actually tell you what's being oxidized and what's being reduced. Notice here that Mg0 is turning into Mg plus 2. Oh, that, as we saw here, is the oxidation. And this is showing you clearly that the Al plus 3 is turning into the Al0, which is what we showed down here. Now, you might remember from when we balanced the half reactions, oh, I have 3 magnesiums and 2 aluminums, but when we did the half reactions here, I only have 1 apiece. Does that matter? No, it doesn't matter. If you want to include those coefficients, if we wanted to if we wanted to include the 3 here, you have to be careful. If I want to say that there are 3 magnesiums, and there are 3 magnesium, well, that impacts the number of electrons. 3 times 1 is 3, 3 times 1 is 3, 3 times 2 is 6. Here, I said down here in a balance reaction, I have 2 aluminums on each side. Well, if I put a 2 here and a 2 there, 2 times 3 is 6. That means positive 6 plus negative 6. 2 times 3 is 6. Now, the reason that I teach this when I teach the half reactions is because I think it's really important that you see that when oxidation loses 3 electrons, it's providing the 6 electrons that the reduction needs. Okay, so I'm going to leave off with this. I'm going to make this part 1 of our video for the Voltaic cell. I'll talk about some other consequences with this, but this is really the most important portion. Thank you.